Okay, thank you very much, Callum. Alright, so I'll kick things off. As Callum said, my presentation will be on the application of oxidants for decontamination of beef during carcass chilling. So today I'm going to run through the significance of the beef industry and some of their issues, my proposed interventions, the results that I have to date, and a bit of a summary and future directions. So currently the beef industry is, the meat industry is quite a highly valuable commodity in Australia, contributing approximately 1% of the total GDP in 2014-2015. And we are currently the third largest exporter of meat in the world. So you may ask, what's the problem? The problem is the contamination of enteric pathogenic bacteria. These include sugar toxin producing E. coli, or also known as STEC. It can be also referred to as EHEC and VTEC, and Salmonella as well. Just as an example, this is an extreme example of a contaminated hide. So that's the undersurface of a cow, and that's quite nasty. So these bacteria pose a great public health risk if the consumers were to eat this contaminated food. So they can cause illnesses such as gastroenteritis and hemolytic uremic syndrome. And in the worst case scenario, this can even result in death, depending on the health status of the individual. These bacteria also pose, they also limit, I should say, the exportation of the beef, depending on where they want to export. So many countries, including the USA, have a zero tolerance policy for EHEC bacteria. So this can limit the exportation to these countries if present. Not only that, they also pose a hindrance, I guess, on the industry reputation. If there was an outbreak, this could severely impact the reputation of that company, and therefore they may reduce their production. So what's being done to solve this problem? So currently the industry employs various technologies during the carcass chilling process, during the process I should say. These include water washes, organic acids such as lactic acid, and even trimming the carcass if it's visibly defective. So however, they're not always 100% effective, and this drives the need for a more effective and reliable way to decontaminate the beef. So previous work has indicated that during the chilling process, the numbers of bacteria are reduced. It's not significant, but it is still valid. And a member of the Food Safety Centre investigated this more, and he studied the behaviour of E. coli during the carcass chilling process and found that E. coli become more susceptible to oxidative damage during the chilling process. So then he further went on to investigate a safe and food-approved oxidant, chlorine dioxide, to decontaminate the beef, and found that it reduced the bacterial load below the detection limit. This further backed up that E. coli becomes more sensitive to oxidative damage during the chilling process. So therefore my aim was to evaluate and investigate the efficacy of other approved oxidants during the process, during the chilling process, to reduce the pathogenic load of bacteria, while comparing them to commonly used organic acid, lactic acid, in the meat industry. So my approach was to use, firstly I did studies using a simple broth system, using 150 parts per million peroxyacetic acid, which is also an oxidant and food approved, and comparing those to lactic acid. And then we moved up to a more complex system in an incubator. As you can see there, it's rigged up, well you might not be able to see, but it's rigged up with a chilling a spray using a pump and a reservoir outside. So just into more detail, during the broth challenge study, we used E. coli and Salmonella as the test organisms. These were then exposed to a simulated chilling process in the water bath, and at 3 time points during the chilling process, aliquots were removed and treated with either peroxyacetic acid or lactic acid. During the chilling process, the times being varied, we took samples and serial diluted them, and then spread plated them and enumerated them. And as you can see, there's quite a nice spread plate just on the bottom. So these are my results that I got for using peroxyacetic acid, about 150 parts per million. So on the x-axis you've got time in hours, and on the y you've got the log reduction of E. coli. So the purple data set is the treatment at 40 minutes. The red data set is the treatment at 6 hours, and the green data set is treatment at 24 hours. And as you can see, they were all reduced below the detection limit, which is that black dotted line, within 24 hours. I think the 24-hour treatment reduced it in 28 hours from the initial treatment time. So this graph actually represents all of the strains tested. So it showed this pattern throughout all the strains tested. So just as a side, the inactivation rates were faster in broth when compared to chlorine dioxide, as I mentioned in the previous study. And as you can see there, they're about 10-fold higher for the inactivation rates. So in the same system, using lactic acid at 3%, just again at 40 minutes, at 6 hours and 24 hours, you can see that the E. coli numbers didn't really change over the course of the experiment. And this experiment ran for approximately 3 times longer in terms of the hours that we tested. So then we moved on to a meat challenge study, and this is where we carried over peroxyacetic acid to do the meat challenge study. So the meat portions were painted with E. coli, as you can see in the top right corner there. These were then put in an incubator and subjected to a spray chilling process. So the incubator was rigged up with a pump and a reservoir containing either water or distilled water as the control and peroxyacetic acid as the treatment. And these would spray every 15 minutes for 32 cycles. And at 4 time points during the chilling process, we took samples. So we swabbed them in 2 places on the lean and the fat side, and then enumerated them. So these are the results I got for the meat challenge study. So as you can see, the peroxyacetic acid achieved approximately a 4 log reduction within 72 hours on the fat side, with the orange being treated and blue being control. And on the lean surface, it wasn't as effective. This may be due to the fact that on the lean surface there's a lot more places where bacteria can hide and attach, so they're more able to get a good grip on and may not be killed or wash off. Just as a comparison to chlorine dioxide, chlorine dioxide did inactivate faster on meat. So as you can see, it reduced by approximately 4 logs within 24 hours, but remained steady to 72 hours. And it's followed a similar trend on the lean surface as well. So just to wrap things up, so in summary, peroxyacetic acid reduced the bacterial load in broth and on meat by more than 5 logs and 4 logs respectively. Peroxyacetic acid has a faster inactivation rate than chlorine dioxide in broth. Lactic acid treatments results demonstrated that E. coli aren't sensitive to acid stress during the chilling process, and E. coli are susceptible to oxidative damage during chilling. So in the future, this research could investigate into more novel oxidants in the intervention technology. I'd like to see sensory analysis and quality evaluation done, because while we know it does work on reducing bacteria, we don't know if it has adverse effects on the meat itself. Then move up to maybe an industry trial and ultimately the implementation of this into the industry itself. Finally, I'd like to thank my supervisors Tom and Jay for being great support throughout the year, providing constant advice and answering all those silly questions that I may have. MLA for being the sponsor and funding agent for this research. Michelle for constant advice as well throughout the lab, and just little bits and pieces that great help throughout the year, and also the prepper and staff Laurie Mange, because they're great too, giving me chemicals when I need them and things like that. So yeah, thank you very much. Any questions?
Well done, Zach, and way to start off. We finished 50 seconds early. That's great. Questions from the floor for Zach?
Do I have a general question about the area, rather than specifically about what you were saying? I mean, you're aware of Kevin's law in the United States that's trying to put through to deal with these E. coli in hamburgers that killed a little boy called Kevin. I just wondered.
No, I'm not.
They come out from, I think, from the acid in the stomach of the cow that allows E. coli to live longer there in feedlots. I guess my question is this the sort of thing we have in Australia or not? Do we have those very super acid-resistant bacteria in our meat chain? I know we're mostly grass-fed, but we do have some feedlots.
That's a good question. I'm unaware at the moment. I know that the pathogenic bacteria can be introduced during either hide removal or evisceration, which is the removal of the intestines and stomach and things. So maybe if the stomach was punctured and that was to go onto the meat surface, maybe that could be an introduction to acid-resistant bacteria.
Right.
But I'm not sure if we have them in Australia.
Okay. Thank you.
There's a fairly strong trend to have more dry aged beef now in restaurants.
Yes.
Is that potentially a more dangerous situation the longer you leave the meat?
So, from what I've read in the literature, drying the meat, so causing surface desiccation, actually reduces the water activity. So that reduces the amount of water that's available to the bacteria. So therefore, they may not be able to grow. If kept under correct conditions, I don't see why that should be a problem.
Any more questions?
Was one of the things you said sort of towards the beginning that lactic acid is widely used, but you guys actually found it wasn't very effective?
Yes, so it is used, but during the chilling process, it's not necessarily used during that process. It's used.
Right. It's the color of the chilling.
Yeah, it's used as a different decontamination step, but we used it just as a comparison because they commonly use that in the industry.
Just had one quick question. I mean, you were saying you want to go on and ideally do sensory testing, that sort of thing, but just direct observations of your slabs of meat. Was there visible oxidative differences between them?
So I did this 3 times, and it changed every time that I did it. So one time the control would look fantastic, another time the control would look just the same, and it's variable, I guess. So we need to optimise that and then take it further, I guess.
Okay, any last questions? Thank you very much, and well done for your questions.